case any of you need reminding, we've got the midterm exam on Thursday in this room, 8 a.m. sharp. I'll be here about 10 to 8. Get everything ready. I'll have some spare paper and pencils in case anybody has forgotten. So we'll start at 8 a.m. on the dot, 8 till 9:30. Okay, so today we're doing the, and again as a reminder, so what we're doing today in class is not going to be on the exam on Thursday. Okay, all right, good. So we're doing now the complex Klein-Gordon field. And complex Klein-Gordon field. So again, you know, we're accelerating now. You know all the formalism. You know how to apply this. So, but if we just imagine that you haven't seen this before, and you want to look at the looking at the Klein-Gordon equation, where phi is complex. So phi star is not equal to phi in general. Phi is complex. So what do you do? So here we're talking about at the classical level. Imagine a classical complex field obeying the Klein-Gordon equation. So what do we do? Well, the first thing we do is find the Lagrangian density that gives you that wave equation. So it turns out, we should have seen this, we've seen this previously, phi comma alpha, phi comma beta, minus m squared phi star phi. But this Lagrangian density, hang on, have I done that right? So, oops, sorry, there's a star missing. So, phi star, comma alpha, phi comma alpha raised, phi comma alpha star. Okay, so the Lagrangian density, by the way, L is always real. Okay, you integrate the Lagrangian density over space, you have the Lagrangian, you integrate over time, you get the action. The action is a number, a real number is always real. And maybe I can just mention there's not something particularly important for us in this course, but and a Lorentz scalar. There is a theorem that if the Lagrangian density is a Lorentz scalar, then you are guaranteed. So when I say it's a Lorentz scalar, I mean if you transform, if you do a Lorentz transformation to a moving frame, then this transforms as a scalar. Okay, that's what I mean. And you can see that, well, phi is a scalar field, so this construction here, phi is a scalar field, then this construction here is a scalar. Now, it's important to note this because this implies that the quantum field theory is Lorentz covariant. So there's a general theorem. This is why people like to start with, or one reason why people like to start their quantum field theory with writing down a Lagrangian density. Because if the Lagrangian density is a scalar under Lorentz transformations, then you're guaranteed that the quantum field theories that you construct from it will be Lorentz covariant. Anyway, moving onwards and upwards, here we treat phi and phi star as independent fields. Those of you who feel nervous about that, you can always write equivalently, you could write phi in terms of its real and imaginary parts. I put in a factor of root 2 for convenience. We'll see later there's going to be an exercise the homework problem where you actually rework. If you write phi like this, where phi1 and phi2 are real, if you plug this in here, you find the Lagrangian density becomes just a sum of two Lagrangian densities for two real Klein-Gordon fields. So we've already done the real Klein-Gordon field. You'll find that you just have two of them, phi1 and phi2, and you can do the development that way. It's completely equivalent. All right, so anyway, so this Lagrangian density, if we do treat phi and phi star as independent fields, we get two Klein-Gordon equations. Let's write it as box plus m squared phi is 0, and box plus m squared phi star is 0. There we go. So you can confirm that, you can check. The Lagrangian density gives you the Klein-Gordon equation for phi and phi star. And so we're in. We've got a Lagrangian density that correctly gives us the Klein-Gordon equation. So now we can start looking at the momentum density conjugate to canonical momentum density conjugate to phi is by definition equal to this, the partial derivative of the Lagrangian density with respect to phi dot. So if you look at that, if you look at the time components here, you should see that, well, this is going to be equal to phi dot star. Phi dot star. Whereas the momentum density conjugate to phi star, which by definition is equal to this, partial L with respect to phi dot star, this comes out to be phi dot. And as I mentioned before, just for easier notation, it's common just to write pi is phi dot star. Instead of having this index phi, we just write it as pi. And this one here, notice that this is equal to the complex conjugate. I mentioned this before, but I'm mentioning it again just to make sure you don't get confused. The momentum conjugate to phi star turns out to be the conjugate of the momentum, turns out to be the complex conjugate of the momentum conjugate to phi. Anyways, instead of these just a bit fiddly, so you may as well just write them as pi and pi star. Okay, this is the way it's commonly written, the way the book writes it, the way almost everyone writes it. So this is the momentum conjugate to phi, and it's equal to phi dot star. This is the momentum conjugate to phi star, and it's equal to phi dot. All right, so now let's see. Do we need to write down? Okay, we can do that later. All right. So from here we can get the we can get the Hamiltonian. So the Hamiltonian, which is equal to the integral overall space of the Hamiltonian density, is equal to pi r phi. Well, actually, let's write it like this. Let's write it as pi phi dot plus pi star dot star minus the Lagrangian density and p hat p. Pi grad phi plus pi star grad phi star. Okay, so in these expressions you have things like what you normally have. You write it like this. For instance, this term here. You have, when you have a collection of fields labeled by R, then you're summing over R. And of course, our fields here are phi and phi star. So this sum over R, this is just phi dot plus pi star phi dot star. Okay, that's where that comes from, the general expression for the Hamiltonian. Remember, we have sum over our sets of fields. Here, our set of fields is just phi and phi star. Okay, so we have this here, and we have an expression for the momentum. Phi grad phi plus phi star grad phi star. All right, so we've basically written down the classical theory. Now we quantize. So to quantize this theory, so no one's left a bomb here. This is a bomb or no bomb? Okay, so to quantize, we have to write down the equal time commutation relations. Time commutation relations. So remember what they are. They are written in terms of, imagine I have just a general set of fields. Running out generally, I have some fields phi R, phi with the label R, and their conjugate momentum densities. So what does this mean? This means that in this case, if I take the first field, which is just phi, so what do I have? I have phi hat xt. What is the momentum conjugate to phi? It is just phi dot star, which when you promote it to an operator, it becomes phi dot dagger. So we've got, let's see, that's operator. All right. Phi hat dot dagger x prime t is equal to I delta 3. Rub this up here. Delta 3 x minus x prime. We also have, remember we've got two sets of fields. With the label R. One field is phi, one field is phi star. Let's think about the field phi star. This canonical commutation relation would look like this. It would be, this field phi R would be phi star, in other words, phi dagger. And the momentum conjugate to phi star is just phi dot. So we're going to get phi dot. All right, so I hope it's clear what I'm doing here. This is the general canonical commutation relation for any field and its conjugate momentum. Here we've got two fields, phi and phi star. You apply this relation to the field phi, you get this here. You apply this relation to the field phi star, and you get this here. And it doesn't take an Einstein to see that actually these are exactly the same. If you take, you might want to just check that, if you take the complex conjugate of this, you get exactly this. They are exactly the same thing, okay? So really, this is redundant. All right, it's just the same thing. So we've got this. And of course, the canonical commutation relation also say that phi r commutes with itself, and the pi r's, the canonical momenta, commute with themselves. So in our case, and it's also true that, sorry, there's something I missed. It's also true that important to note that let me write it like this. That the field and its conjugate momentum, sorry, I'm just finding it really hard to concentrate with twiddling the pen. I don't know why, I get easily distracted with sorry, it's funny, thank you. The momentum, and I had a PhD student who used to do that. Whenever we used to sit and meet, he had this trick with his pen. He had a way of flicking it around his hand, and he'd be doing. I just couldn't concentrate. It's never please. Anyway, sorry, but thank you. I'll try now. Don't worry. Okay. The canonical commutation relation between the field and the conjugate momentum of a different field is 0. Okay. So in fact, the way we wrote this originally. Like this with a Kronecker delta. Okay, so the momentum, the field and its conjugate momentum, if R is not equal to S, so if you're talking about I have a field and momentum conjugate to a different field, then they commute. So this is also the case. So if you look at these relations, let me write down the others over here. So you can go through and check this just to make sure. But anyway, we've got this one, this is important, and the others, everything else is basically, everything else is 0. So we have this is of course 0, and it's also true that phi hat xt, phi hat dot x prime t is 0. This is just saying that, remember, this is the field phi, and this is the momentum conjugate to phi star. Okay, so we're saying, remember that the momentum conjugate to phi star is phi dot. So here we're taking this case here. We're looking at the field and the momentum density for the other field, and they commute. Okay, so so that means that phi hat and phi hat dot commute, because this is a canonical momentum for phi star, this is a field phi, they commute. Let's see, it's also true that, so because, in fact I should have written it like this here, sorry, I should have written this like this. The phi, the field commutes with itself, different fields also commute, okay? And different canonical momenta also commute. So this means, remember our different fields here are phi and phi star, or phi and phi dagger. So this means that this is 0. The canonical momenta for different fields are 0. So this is also 0. All right, this is the canonical momentum for phi star. This is a canonical momentum for phi. So they're canonical momentum for different fields, so they commute. So anyway, there are a lot more because you've got two different fields, phi and phi star, with two different canonical momenta. There are a lot more relations to write down that are zero. Now, you don't really need to worry about these because basically the point is all commutators are zero except for this one. Alright, so let's just keep this one here and there we are. As usual, if you wanted to check consistency, you could write down the Hamiltonian operator from the classical expression and from the Heisenberg equation of motion, check that we get back the Klein-Gordon equation for phi and phi star. You know, people don't usually bother doing that because you know that it's going to happen. That's the whole point of using the Heisenberg picture, is that the operator equations of motion are exactly the same as the classical equation of motion. Okay, so let's just take it that we've got Klein-Gordon equation for the operator field, and we have our equal time commutation relations. So all other commutators are equal to 0. All right, so now let's write a Fourier expansion. So expand the solution in plane waves. So we have, I missed anything else? No. Okay, so the expansion is like that of, so again I'm going to write it as, so x is tx and k dot x is omega t minus k dot x. Is that right? We're using the derivative with the time, plus minus minus minus, so k0, that's omega t minus k dot x. Okay. General. This is k0t, and we're taking k0 to equal omega the square root of log k squared plus m squared. Okay, so I'm just going to keep the notation the same. Good. All right, so the plane waves, we're going to write them like this. Here is our expansion. We have a sum over wave vectors, 1 over the square root of 2. There's the normalization volume. As usual, we've got a large normalization volume. Here is omega, and here is the expansion. We have a constant operator ak, e to the minus I k dot x, and you might be expecting me to write down this here. This is what we had for the real Klein-Gordon field. We had a e to the minus I k dot x plus a dagger e to the plus I k dot x. But that would make the field Hermitian. The Hermitian conjugate of this is equal to itself. Our field is not Hermitian, it's complex. So what we in fact have is, instead of an A dagger, we have a different operator B. We have A plus B dagger. And so now phi hat dagger is not equal to phi hat. We also have an expansion for the field operator phi dagger, which is the quantized version of phi star. Now it's a sort of funny thing, you formally treat phi and phi star as if they're independent. So now I've got two fields, phi and phi dagger. But of course, you don't really need to work with phi dagger. You've got the field phi. Phi dagger is just there automatically. So it's just a sort of mathematical convenience, which it's in the long run, you can, as I said, you could just work with two real fields and do this, but it turns out to be more convenient to do it this way, and I'll show you why. I'll show you why at the end. Basically, if you do it with two real fields, then the excitations you get naturally describe positively and negatively charged particles. If you do it with two real fields, to get the particle interpretation, you'd have to take some funny linear combinations of those real fields. I'll show you, there's an exercise that you're going to be doing for homework to illustrate this. But anyway, so just going on. But if you've got the expansion for phi, so obviously the expansion for phi hat is just the conjugate of the Hermitian conjugate, and it's redundant to write it down, but let's write it down anyway. You take the Hermitian conjugate, you get b hat k e to the minus I k dot x plus a hat dagger k e to the plus I k dot x. There we go. So now, here is here's an optional homework problem. Optional homework. So you've done similar problems if you've been doing the homework, that is, you'll have done similar problems already. But the optional homework is to take this expansion, to look at the expansion look at this expansion, sum over A's and B daggers, plus canonical commutation relations. So in other words, this here plus the fact that all the others are 0. And what does this imply? This implies, so what am I saying? If you take these field expansions and you take the canonical commutation relations for the fields together, they imply the following relations. For the A's and B's. So here we have the commutation relation of A and A dagger. Here we have the commutator of B and B dagger. And you see you get the usual result that you're used to from the harmonic oscillator. And of course, the all other commutators are 0. So what do I mean? I mean that of course AK with AK primed is 0. AK with BK primed is 0. The B's, etc., etc. Also the A dagger K with B. In other words, you've got these A's and A daggers, B's and B daggers. They all commute with each other except A and A dagger, B and B dagger. Okay? So A dagger and B commute, A and A commute, B and B commute, B and A dagger, they all commute. The only ones that are non-zero are A and A dagger, B and B dagger. Now if you look at this, what does this mean? it means that we have, so, you know, you can go through that if you like. It's similar to the sort of thing that you've done already, but just a bit more involved to derive. So what does this mean? What we have are now two sets. We have two sets of annihilation and creation operators. For two different types of field excitations. Or what are heuristically called particles. Two sets of annihilation and creation operators. So if you like, you could call them the A type and the B type. We've got two independent, and of course these, remember, the A's and the B's commute among themselves, so they're completely independent. I've got annihilation operators for A and A dagger, and then I've got B and B dagger. So I can define, well, I can imagine, I think that the A's and the A and A dagger annihilate and create one kind of particle. For B and B dagger annihilate and create a different kind of particle. And I can define number operators. Number operators. So I can call this, so let's call it NAK is A dagger K AK, and then a number operator for the B particles. B hat dagger K, B hat K. A dagger A, B dagger B. All right, and again, the eigenvalues. Right, each of these number operators has eigenvalues, 0, 1, 2. So what I have, what we have, so now for each mode, mode K, there are now two sets of energy levels. So if I'm considering just one particular mode K, I have the A type, and I have the B type. So I can say, well, I can be in the ground state, or I could be excited here, and here I go up and down, depending on whether I apply A or A dagger. And the raising operator raises me up a level, the lowering operator lowers me down. Here I can go up and down with B and B dagger. I've got two independent sets of energy levels, which can be independently excited. So basically there's a sort of doubling of the energy levels. For each wave vector K, instead of having just one harmonic oscillator, I've got two harmonic oscillators. You can think of it like that. So two oscillators for each K. So the vacuum, so the ground state is now defined by the following, that the annihilation operator for both types of particle annihilate the state. Okay, so the vacuum, you would say, well, I'm in the ground state. This would be the vacuum. Both oscillators for every wave vector k, both oscillators are in the ground state, and then of course I can have excitations. I can have an excited state, excited states. So, for example, let's say the following. So here I've got an A-type particle with momentum k. So here I would have, well, I've written it slightly, so I'm looking at two different modes. I'm looking at two different wave vectors. I'm saying that for the wave vector k, the A-type oscillator is excited. For the wave vector k primed, so not written this very well, this is the A-type and B-type. So I can imagine I'm looking at, so each mode, each wave vector, there are two oscillators. Imagine I take two different wave vectors, k and k prime. For one of them, the A-type is excited, for the other one, the B-type is excited. So I'd say, well, I've got an A-type particle with momentum k and a B-type particle with momentum k prime. This kind of thing. And of course, you can build this up and excite all kinds of modes as you want. Here's one more optional homework. You want to check this, that if you look at your expressions for the Hamiltonian operator, we wrote these down before. Just write it like this. So here is in operator form. And here I'm writing it as if we've got a collection of fields labeled by R, our two different fields of phi and phi star. Anyway, if you write down your expressions for your Hamiltonian and momentum operators, and you substitute in the field expansions, which I've erased, you can show, and I'll tell you, right, this is an optional homework, if you feel like checking this, that the Hamiltonian operator comes out to be the sum over k of h bar omega, put in an h bar for familiarity. Here are the two types of number operators, which whose definition I've also rubbed down, but anyway, I have the, so I'm just summing, so of course the number operator, which the A's and the A daggers, so this is just okay. So if you take the expansions for the field in terms of the A's and the B daggers, and you substitute into here and do the integration, you should find that you get this expression. The total Hamiltonian operator can be written in terms of the AA daggers, the BB daggers. In other words, it's just the sum of the number operators for each mode times the, what we interpret as the energy of a single excitation of that mode, and the momentum operator, the total momentum of our complex Klein-Gordon field comes out to be the sum over K. I should have mentioned, this is after normal ordering. After normal ordering. So we're redefining. We take the normal product here. So that is why there's no factor of a half. There's no, you may be thinking, hang on, what happened to the vacuum energy? What happened to the zero, there's the term, the factors are half here that give the divergent vacuum energy. They've gone away because we've taken normal ordering here. The total momentum operator comes out to be the sum over the modes, h bar k, and again, times the number operator, the sum of the number operators. So here you see the physical interpretation, the interpretation in terms of particle-like quantities makes sense. You can say, well, like for instance in this case, if I've got one particle, if I've got the K mode, I have an A-type particle, an A-type mode excited, whereas for the K prime mode, the B-type is excited. Then, the total momentum is going to be h bar k plus h bar k prime. So I can think of it as, I've got a particle of this momentum and the particle of this momentum, and the total momentum is the sum of the two. Similarly, the energies add, in this sense, the total energy is just the numbers of these so-called particles present times their energies. So you can think of it as, well, there are two types of particles here. There are these field excitations describe two types of particles, but now the interesting part comes when we consider the charge. So the charge, let's look at the charge operator. So we are advanced quantum field theorists. So remember our Lagrangian density. Classical Lagrangian density is invariant under phase transformations, by which we mean phi goes into phi prime, which is epsilon phi, for say for small epsilon. Okay, this is the Lagrangian density is invariant under such transformations, and I also, of course, put phi star is invariant, and so from Noether's theorem, this implies a conserved quantity. Conservation of charge. And from what we did before, the charge operator takes the following form. If you go back and you look, well, we did this, we've done this already, minus IQ times the integral over all space of the following. We have a phi hat dot dagger, phi hat minus phi hat dot phi hat dagger. So minus IQ, integral over all space, we have a phi dot dagger, phi minus phi dot phi dagger. So if you recall the general expression that we had way back from Noether's theorem, looked like this, you would have phi phi hat minus pi hat dagger, phi hat dagger. And of course here pi hat is phi dagger. Pi hat is phi dot dagger. So pi hat is phi dot dagger. And pi dagger is phi dot. Because of course classically pi is phi dot star. And pi star is phi dot. Okay, so I hope that's clear that when you quantize them, then pi becomes phi dot dagger, and pi dagger becomes phi dot. Okay, so that was the expression. Anyway, so this is the expression for the charge operator. So now I have a homework problem. This one is not optional. This is an important homework problem because it's different from different kind to the ones you've done before. If you take, remember we have field expansions for phi and phi dagger in terms of plane waves, written in terms of the A's and the A daggers. I can substitute the field expansions. Substitute. So we have these field expansions. Schematically, phi, so okay, A's and B daggers. Substitute these expansions into here, do the integration, fiddle around. You should be able to show that the charge operator comes out to be the following. Q times the sum over K. Now you might be expecting me to write down NAK plus NBK. Okay, you might be thinking that the total charge operator is going to be Q times the sum over modes, the number operator for the A-type particles plus the number operator for the B-type particles, because got all these different particles, it's going to be just like here, right? Ah, no! It turns out there's a minus sign. Here there is a minus sign. So now, it's interesting that you see here that the interpretation for the energies and the momenta is that, well, I've got so and so many particles with the energies h bar omega, momenta h bar k. Total momentum is just the sum of the numbers times those momenta. It's easy. Here, what is going on here? Why is there a minus sign? There is a minus sign because the A-type particles have charge. Charge plus Q, whereas the B-type particles have charge minus Q. That is the interpretation of this. If I've got n particles of A-type, well, then in a given mode, then the total charge is just Q times that number. If I have n particles of B-type, the total charge is n times minus Q. Okay, so I'm summing up, I've got n particles with charge Q, and I've got Na particles with charge Q, and Nb particles with charge minus Q. So what we have here are particles, what are commonly called particles, and antiparticles. Particles and antiparticles. Now, so apart from the charge, so you have two types of particles whose properties are the same, the mass is the same, the kinds of momentum and energies that they can have are the same, but the charges are equal and opposite. Now what we have, we're looking at the case of, let me just maybe draw this out, the example that we're looking at. So we're looking at the complex Klein-Gordon field. We haven't discussed the spin, but this is there is no spin, no intrinsic angular momentum. So don't worry about this too much now, just to mention briefly. Remember I said from symmetry under rotations, you can derive conservation laws for angular momentum, and there's an expression for the intrinsic spin. This is a complex scalar. This is a scalar field. A scalar field has no spin. So with the particle-like excitations here have no spin, but they do have charge because it's a complex field, and you can have positive and negative charged particles and antiparticles. Later on, when we do the Dirac field, the Dirac field is complex, and it's a spinor field. It has 4 components. It's not a scalar, and it has spin. And what we will find is you'll get, so because of the extra components, the particles have spin, so there's an added feature. But because the field is complex, and you also have, as in the complex Klein-Gordon field, there is a phase symmetry. This is a complex field, and you have also particles and antiparticles, which are just electrons and positrons. So in other words, what I wanted to say here is that you can think of this, what we've done here for the Klein-Gordon field, the complex Klein-Gordon field, it's a bit like the Dirac field but without spin. It's a sort of simplified version. So you could think of these A-type and B-type particles as a bit like electrons. If you imagine a world in which electrons and positrons didn't have spin, then this is probably what it would look like. When we come to the Dirac field, we're going to find a similar feature. There are 2 types of particles with opposite charges, but there's the added complication that the particles have spin. And these particles are what we call electrons and positrons. They're spin-half particles with equal and opposite charge. So this generally happens in quantum field theory. When you have a phase invariance and there's a conserved charge, you find that there are particles and antiparticles with equal and opposite values of the charge. So I highly recommend you do this homework problem and check that there really is a minus sign here, because if there's no minus sign, then everything I said would not make sense. Let's see, I have one other little thing to say. There we go. So there's another homework problem I recommend you do, and that is homework So exercise 3.2. Exercise 3.2. So it's a nice exercise 3.2 because so what you're asked to do is to write the field. So let's look at our operator field. We've got a complex Klein-Gordon field, and let's write it in terms of two real fields. So we have two real fields. Phi1 and Phi2. Now, what you do in exercise 3.2 is you show what you have are two independent. So if you look at the Lagrangian density, if you write the Lagrangian density for the complex Klein-Gordon field in terms of these Phi1 and Phi2, you find that you get just a sum of two terms. I have two Lagrangians for two independent real Klein-Gordon fields. So I have two real Klein-Gordon fields. And what I can do for each one, so for each one, I can write my usual expansion. You remember we had so here I'm just sketching for you what you're asked to do in the homework problem is you have, so here we've got two independent real Klein-Gordon fields labeled by R as 1 and 2. For each one we can do the usual expansion with A and A dagger, okay, because it's a real field. And what you can show is you can show that so here you've got, hang on, I can think of the same system as two real fields, but real fields don't have any charge. What happened to the charge? What you can show is that the operator A that we obtain from the expansion of the complex field. In other words, this is the annihilation operator for the A-type particles with charge plus Q. Can be written like this. K1 plus I A hat K2. And the B, the annihilation operator for the B-type particles. Minus I can be written like this. So here is a funny thing. That if I think of this system, if I say, forget about, I don't like these complex fields, I want to work in terms of two real fields. I've got the Phi1 and Phi2, I've got two real fields, and for each one of them, I can define annihilation and creation operators. I could think of excited particle-like states for these two real fields. It turns out that if you want to describe a particle with a charge, So let us say you wanted, for instance, to consider the following state. Okay, I act on the vacuum with my raising operator for an A-type particle. So I get a particle with charge plus Q. If I think of this in terms of my two real fields, this is going to be equal to so I'm taking the Hermitian conjugate of this relation here. In other words, it's 1 over root 2 sorry, I've got a dagger here. So what does this mean? It means that if I look at the two real fields and I say, let's take an excitation where I have one particle present for this real field, and I take an excitation where I have one particle present for the other real field, and I take this linear combination, that gives me a state with charge plus Q. So in other words, I'm making this sound a bit more complicated than it is that the annihilation creation operators for these two real fields don't describe charged particles. You have to take linear combinations of those states in order to get a charged particle. So this is why we work directly with the complex fields. You might think, I don't like this, I want to work with the real fields. But then, if you want to describe, particle-like states that have definite charges, you would have to take linear combinations. I would have to say, okay, here's the particle state I'm interested in. It is a linear combination of an excitation of this real field and an excitation of this real field. I have to combine them in this funny way. It's just not worth the bother. So that is why, in the end, we do it with the complex fields. But you don't have to. You could think in terms of real fields, and in which case the particle-like excitations that we see that have positive and negative charges would be linear combinations of the particle-like excitations of the two real fields. Anyway, there's exercise. There's also something that you can do at the end of exercise 3.2, where it says, well, if I think of this system as two real Klein-Gordon fields, you can write down commutation relations for your real Klein-Gordon fields. It's just like the commutation relations that we did before, except I've got two copies for two different fields. From those commutation relations, you can derive commutation relations for the phi and phi dagger. And you should get the commutation relations that we've been working with. Okay, so from commutation relations for phi 1, phi 2, you can derive the ones for the. Just check that it's all consistent. It's a good exercise to do. Let's see, I think. There we go. Anyway, so when you've got conserved charges, it's just simpler to work directly with the complex fields. So there we are. Thursday, there's the exam. The next week, we're going to continue. That's all for today. Are there any questions? Okay, so please do the homework. Please do exercise 3.2, and please do that homework where you're asked to derive the charge operator in terms of the number operated with a minus sign. I will be here 10 to 8 on Thursday morning, ready to blow the whistle. The whistle blows at 8 a.m. You've got 8 till 9:30. And if anyone has any last-minute queries, email me. I have an office hour today or tomorrow. It's not too late. If you haven't understood anything and you want me to explain it all to you again, well, we can try and do it in an office hour. All right, thank you. So see you Thursday.